In this video, we are going to talk about solutions of consistent systems, systems of linear equations that have a solution. We'll start with an introduction, and essentially we're asking the question, can we determine which of the three outcomes that a system has no solution, infinitely many, or unique solution? Can we determine the outcome without actually solving the equation? We have a theorem here to help us with that, to tell us when we might have infinite solutions. And then we also look at homogeneous systems. That's when B, our B vector, or all these equalities are equal to 0. We have theorems to tell us when there can be infinitely many non-trivial solutions. If we recall, in a previous video, we talked about how systems of linear equations either have a unique solution, infinitely many solutions, or no solutions. And so we want to know if we can determine which of these three outcomes will be likely without actually solving the system of equations. So for example, and we'll do a geometric example, if we have a 2 by 3 linear system, so here's our first equation, three unknowns, x1, x2, and x3. So we have two equations, three unknowns, and these are all linear. So these two equations are equations of a plane. So geometrically, similar to the example we had before with lines, but geometrically the planes might be parallel, in which case there are no solutions. They might be coincident, or the same planes, in which case there are infinite solutions, or here, when we have two planes intersect, they intersect in a line. So this yellow line here is the intersection of these two planes, and the planes go on forever. And so every point on this line is a solution to the system of equations. Since the line is infinitely long, there's an infinite number of solutions when the two planes intersect. In this case, in the case of a 2 by 3, there is no possibility for a unique solution, for one solution. It's either infinite or no solutions. Another example of determining which of these outcomes, the three outcomes, is likely without solving the equation comes from previous examples and previous videos, which suggested that the presence of a free variable indicates infinitely many solutions, because remember, if a variable is free, it can take on an arbitrary value, an infinite number of values, and therefore will give the system of equations infinitely many solutions. So we're going to look at this case, this example again, but first we're going to kind of formalize a few things. We will start with this theorem. The number of free variables in a consistent system, so you should note that this does assume a consistent system, equals the number of unknowns minus the number of non-zero rows. So this is just kind of how I shorten the theorem, but this is the full theorem here, starting with let A slash B be the augmented matrix for a consistent system of linear equations in n unknowns. So this is the matrix A, that's the matrice of coefficients, and B is the solutions, the other side of the equal sign. So that's the augmented matrix. Further assume that the augmented matrix is row equivalent to a matrix C slash D that is in echelon form and has R non-zero rows. Then R less than or equal to n, because of course you can't have more non-zero rows than you have rows. So R has to be less than or equal to n. And in the solution to the given system, there are n minus r free variables that can be assigned arbitrary values. So this theorem tells you how many free variables there will be in a consistent system. And again, it's the number of unknowns minus the number of non-zero rows in the echelon form matrix. And here's an example. I have my m by n, so I have four equations, 5 unknowns. My first equation is 2x1 minus 3x2 plus x3 minus 3x4 plus 2x5 equals 6. My second equation is 2x1 minus 3x2 plus 5x3 minus x4 plus x5 equals 8. Then I have my third equation is 4x3 plus 3x4 plus 2x5 equals 3. And my fourth equation is minus 2x1 plus 3x2 plus 3x3 plus 3x4 minus 9x5 equals minus 6. So this matrix here. Here is the augmented matrix. This is the matrix of coefficients, and here's my B vector here. So this is my augmented matrix, which is row equivalent to this matrix here. So I haven't shown you all the row operations, but you'll have to take my word for it. So again, the augmented matrix is 2 minus 3, 1, minus 3, 2, 6, 2 minus 3, 5, minus 1, 1, 8, 0, 0, 4, 3, 2, 3, and minus 2, 3, 3, 3, minus 9, 6. And here is the echelon form, 2 minus 3, 1, minus 3, 2, 6, 0, 0, 4, 2, negative 1, 2, 0, 0, 0, 1, 3, 1, and then the last row is all zeros. So this echelon form matrix represents this system of equations here, which is 2x1 minus 3x2 plus x3 minus 3x4 plus 2x5 equals 6. The second equation here, represented by the second row of our echelon form matrix, is 4x3 plus 2x4 minus x5 equals 2. And this last row is x4 plus 3x5 equals 1. Actually, the very last row is 0, so that's just 0 equals 0, which isn't interesting. So when I look at this, I can make x5 my free variable and then solve for x4 in terms of x5. Then I have x3 is solving for that. I can solve in terms of x4 and x5, but then my x4, I can plug in what I solved for in terms of x5, so I can get x3 totally in terms of x5. But what you see here, when I try to solve for x1, I can solve in terms of x5, and x4 and x3 can also be put in terms of x5, but x2 cannot. So x2 I'm going to let be another free variable, and then I can solve x1 in terms of x5 and x2. So what I have is two free variables, and according to my theorem, for a consistent system, the number of free variables is the number of unknowns here, that is equal to 5, minus the number of non-zero rows in the echelon form matrix, which we have 3. That means we're expecting two free variables, which is exactly what I got when I solved this system. So I solved this system just to review how to do this, and also to confirm that my theorem was correct. So I actually didn't need to solve it, I just needed to convert to echelon form, and then that would have told me there were two free variables. Oh, and then I should also add that the two free variables can take on any value, the x5 and the x2, which means they can take on an infinite number of values, which means there's an infinite number of solutions. So I squished this example here that we just did right underneath the theorem. So the next thing we want to do is kind of go over the 3 possibilities for a system of linear equations, and we're going to compare that to what our theorem tells us. First, the system can be inconsistent and have no solution. So this really doesn't concern our theorem since this is about consistent systems. But we do know one possibility is to have no solution. If the system is consistent and r is less than n, because r is always less than or equal to n, so in the case that r is less than n, then there are n minus r free variables, and the system has infinitely many solutions. And then last, the system could be consistent and r equals n. In this case, there are no free variables, and the system has a unique solution. So this is important to remember. And actually, as well as this theorem, this is an important theorem to remember. But hopefully you'll get to the point where these two facts come naturally to you. It's not something you actually have to brute force memorize. Hopefully working with enough examples, it'll be something you just have committed to memory. With this theorem is another important corollary, which is to consider an m by n system of linear equations. So m equations, n unknowns. If m is less than n, you have less equations than you have unknowns, then either the system is inconsistent or it has infinitely many solutions. And I have this here in our overview slide that we want to note the proof. So I didn't have space to put the proof, but we will go over the proof, and it is a proof that you should be able to come up with as well on your own. For our proof, we're going to start by considering an m by n system where m is less than n, since that is the condition given in our corollary. If the system is inconsistent, then the proof is done. Okay, so there's two cases. The system is inconsistent, in which case our proof is done, because we either have to show the system is inconsistent or it has infinitely many solutions. The second case is if the system is consistent, we want to show it has infinitely many solutions. But if the system is consistent, this theorem up here applies, and that means there's going to be n minus r free variables. But we want to be sure that n does not equal r. Well, it is clear that r is less than m, since m is the total number of rows and r is the number of non-zero rows. So r has to be less than m. And since m is less than n, we must have r is less than n. So there are n minus r free variables, and n minus r is greater than 0. So that means the system has infinitely many solutions since it has free variables, and the proof is done. So we will continue with some examples of this corollary, such as, what are the possibilities for the solution set of a 3x4 system of linear equations? If the system is consistent, what are the possibilities for the number of independent variables? So here we have 3 rows, 4 unknowns, and by our corollary, that means if m is less than n, which it is here, so since m is less than n, by the corollary, the system is inconsistent or it has infinitely many solutions. If it is consistent by this theorem over here, the number of free variables is equal to n minus r. So if n is equal to 4, then r can equal to 1, 2, or 3. So the number of free variables can be 3, 2, or 1. So again, the possibilities for the solutions for the first question, it is either inconsistent or it has infinitely many solutions. And then if it is consistent, the second part of the question is, what are the possibilities for the number of independent variables? And they can be 3, 2, or 1. And I'm sorry, I should also define independent variables is the same thing as saying the free variables. The independent variables don't depend on anything else. Another example, what are the possibilities for the solution set of the following 3x4 system? So 3 equations, 4 unknowns. So one thing to notice, since this is equal to 0, all 3 equations are equal to 0, if we set all the variables 1, 2, 3, and 4 equal to 0, there is a solution. So the system is definitely consistent. Since m is equal to 3 and n is equal to 4, by this theorem here, since m is less than n, or actually by this corollary, this system is either inconsistent, which we've already shown is not the case, so it must have infinitely many solutions. So that is our conclusion. Therefore, there are infinitely many solutions. Our next topic is going to be on homogeneous systems. And a homogeneous system, you could say homogeneous system, is where our b vector, this everything is equal to, so b1, b2, b3 up to bm, is equal to 0. So everything here is equal to 0. So our first example of a homogeneous system of equations, this is a 3x4 system, homogeneous system of equations represented by this matrix, this coefficient, this augmented matrix. Here is another homogeneous system of equations, the 2x1 plus 3x2 minus x3 equals 0. The minus 2x1 minus 2x2 plus 3x3 equals 0. The 2x1 plus 6x2 plus 9x3 equals 0. So all of these things equaling 0 make it homogeneous. And the augmented matrix to represent the system of equations is 2, 3, minus 1, 0, minus 2, minus 2, 3, 0, 2, 6, 9, 0. And again, we have all this last entry, this last column is all zeros because it's homogeneous. So the first thing we want to note is the homogeneous system is always consistent. There is always a solution. Do you know why that is? It's like our last example, when we looked at these equations and set it equal to 0, we said there was always a way to find a solution for x1, x2, x3, and x4 such that the linear combination is equal to 0. So we can always solve this homogeneous system by setting x1, x2, x3, and x4 equal to 0. And all the variables equaling to 0 is called the trivial solution. So the homogeneous system of equations always has at least one solution, that is the trivial solution. The other possibility is it can have infinitely many solutions, but it is always consistent, always with at least one solution. And we have this theorem to help us out. So this is about homogeneous systems has an infinite number of solutions when m is less than n. So this is kind of my summary, or my quick summary. And the theorem actually starts here. A homogeneous m by n system of linear equations always has infinitely many non-trivial solutions when m is less than n. I have two examples for you here of this theorem, except it's a little busy, so I'm going to do this on another slide with more room. So my first example has three equations, four unknowns, so 3 by 4. So the first equation is x1 plus 2x2 plus x3 plus 3x4 equals 0. The second equation is 2x1 plus 4x2 plus 3x3 plus x4 equals 0. And the last equation is 3x1 plus 6x2 plus 6x3 plus 2x4 equals 0. And that can be represented by this augmented matrix 1, 2, 1, 3, 0, 2, 4, 3, 1, 0, 3, 6, 6, 2, 0. So again, just the coefficients and then the 0. And this matrix is row equivalent to, so I'm not going to do all the row operations, but it's row equivalent to 1, 2, 1, 3, 0, 0, 0, 1, negative 5, 0, and 0, 0, 0, 8, 0. So this echelon form matrix is represents the set of linear equations over here, which is x1 plus 2x2 plus 3x3 plus 3x4 equals 0. Then we have 0, 0 plus 1x3 minus 5x4 equals 0. And last we have 8x4 equals 0. Back solving, what that gives us is that x4 is equal to 0, and if x4 is equal to 0, x3 must also be equal to 0, so x3 and x4 is 0, which means that x1 is equal to minus 2x2. So what we see is now we have one free variable, x2, which means we have infinitely many solutions. So I solved this to figure this out, but I could have also used this theorem here, which said we have a homogeneous m by n. So in this case, m is equal to 3 equations, 4 unknowns. And if m is less than n, which it is, that means this, since it's homogeneous, it always has infinitely many non-trivial solutions. So infinitely many non-trivial solutions, which agrees with this theorem. So I could do this two ways, by solving it out, or the easy way by using the theorem. Of course, even using the theorem, I have to go through and get this row reduced, this echelon form matrix. My second example with this theorem is the system of equations 2x1 plus 3x2 minus x3 equals 0, minus 2x1 minus 2x2 plus 3x3 equals 0, and the last equation 2x1 plus 6x2 plus 9x3 equals 0. And that can be represented by the matrix 2, 3, negative 1, 0, negative 2, negative 2, 3, 0, 2, 6, 9, 0. And this is row equivalent to the matrix, the echelon matrix, 2, 3, minus 1, 0, 0, 1, 2, 0, 0, 0, 4, 0, which represents, this echelon matrix represents the system of equations 2x1 plus 3x2 minus x3 equals 0, x2 plus 2x3 equals 0, and 4x3 equals 0. Back solving, we have this last equation gives us x3 equals 0, and if this is equal to 0, that must mean x2 has to equal to 0, and if x2 and x3 are 0, this equation, the first equation, tells us that x1 must also be equal to 0. So there's one single solution, the trivial solution. And here, just to look at it, so m is equal to 3 and n is equal to 3, which means here this theorem doesn't apply here. But So it may have infinitely many solutions or only the trivial solutions, but we had just shown that it has only the trivial solution. And I just want to reiterate, in this example, this theorem doesn't really apply because it's talking about when m is less than n, then you know you have infinitely many non-trivial solutions. But in this case, the when m is less than n is not satisfied, so we cannot apply this theorem. Now we've covered the main topics, actually that went pretty fast, of our consistent systems of linear equations. So our goal was sort of to determine the outcome, which of the three outcomes, that of no solution, infinitely many solution, or unique solution, would be without actually having to solve the equation. And first we had this theorem that told us the number of free variables in a consistent system is equal to the number of unknowns minus the number of non-zero rows. And we had this example here that we worked out. We also had the corollary that said for an m by n system of linear equations, whenever m is less than n, then either the system is inconsistent or it has infinitely many solutions. And the proof is something that you should be comfortable generating on your own. We also looked at homogeneous systems. That's where b is equal to 0. And in this case, the homogeneous system is always consistent because there's always the trivial solution, and either has unique solution, that is the trivial solution, or infinitely many solutions. And we had this other theorem to help us out. So a homogeneous system has infinite solutions whenever m is less than n. And we had two examples here. The first one where m is less than n, and so we knew it had infinitely many non-trivial solutions. And then this here, where m and n are both equal to 3, so this theorem did not apply, but we went ahead and we did represented our system with a matrix, did the row equivalence till it was echelon form, and then we saw that we had only the trivial solution. For review, I have two problems, each one with some subparts for you to try. They're actually pretty quick. So why don't you pause the video, give the questions a try, and then on the next slides, I will have solutions for you. These are the solutions. And that is it for this video. Thank you for watching.